Okay, hello everyone. So we will start our seminar today. So the speaker is PhD Dr. Jeong, Uyoung. Okay, so he's recently graduated from AI graduate school. Okay, so received PhD last semester. Okay, last year September, as far as I remember. So actually, he's doing his BS in UNIST and MS in UNIST and PhD in UNIST, and also doing some postdoc in UNIST. Okay. So he's UNIST guy actually. So and also studying HOI, hand-object interactions, and human pose estimation during his graduate school. And today, he will present the seminar on zero-shot text to 3D HY generation, which is actually generating the motion and then object interacting motions from the text. And we are using the keyword of zero-shot because we are sometimes wanting to generate HOI motions for unseen object, okay, and unseen interactions. So in that regard, we are using the term of zero shot. Okay. So, anyways, please welcome him today with big applause. Okay. And yeah, hey, thank you for this lecture today. Okay, thank you.
Thank you. Thank you for the nice introduction. So for this tutorial, I will present the zero-shot text to 3D hand object interaction generation from especially our recently accepted paper. So I'm going to briefly introduce the overall topic and the related fields. So yeah. Text-guided hand-object interaction generation can be defined as these input and outputs. So as an input, we expect to give a text prompt that describes the hand-object interactions, and the output, desired output will be the photorealistic 3D hand-object interaction that aligns with the given input text prompt. So for example, if you give a text input like a right hand eating a hamburger, then we expect to generate a 3D representation of a hand and a hamburger grabbing it. So there could be several applications of this task. So first, we can use this technique to create some 3D contents regarding VR, AR, and in gaming. And secondly, we can use this, we propose this to depth threshold and manipulation. And third, we can use this pipeline to generate synthetic data for training large reconstruction models. So, for example, so the right figure shows the 3D reconstruction of hand and object from a single image. So we might use this text to 3D interaction generation method to further train this kind of models. But there are several challenges in this domain in general perspective. So first is there is not much training data. So it is challenging to train the large-scale generation models that we can usually see in the LLM or stable diffusion. And secondly, we generally in volumetric rendering techniques, they don't have explicit mesh representation. They usually just generate point clouds without any topology. So it hinders the physics space optimization, which is crucial for plausible hand-object interaction. And third, those generated, even if generate object from the text, those objects meshes are very noisy and often include the inner surfaces or intersection, which results in noisy vertex nodes and base nodes, and which can cause problem when you directly optimize those meshes. So I pick for that is related to HY generation. So the first one is zero-shot 3D asset generation, which is a very general test. So it is text-based, so it generates from the text directly. And because it's a general asset, it doesn't have any interaction in consideration. And these are the related works in this build, prolific dreamer, which is a LERR-based, and Gaussian dreamer based on Gaussian H3D, which is a efficient version of Gaussian dreamer. And there are zero-shot-based human object interaction generation methods, which adopts this technique. So it is also text-based, but for the previous works, they all use NERD-based representation, which is one type of volumetric rendering technique that doesn't include explicit mesh representation. So they don't actually ensure physical plausibility in their generation journey. And third build is learning-based end-object interaction generation, which differs from these two above texts. So it is a learning-based, but usually it requires template object mesh as an input, and because it is based on, it relies on the training data set, so it's hard to generalize to unseen objects and interactions. So the related works include GHOP, which is a 3D HY generation without motion, and text to HY, which includes motion generation, and latent HY, which improves the text HY using LDM methods. And last one is zero-shot end-object interaction generation, which I would like to discuss. So it is text-based. So compared to these learning-based methods, we directly generate 3D HY from text, and it also includes interaction plausibility. Because this one is a regression-based, it does not further refine the interaction after they generate, but we additionally refine the interaction. So I would like to briefly discuss the basic ideas and their limitations in those each specific field. So first, zero-shot 3D generation. So in zero-shot 3D generation, they usually use volumetric representations to render the 3D, mainly using stable diffusion files. So stable diffusion models generate 2D images from text, but some of the works extend their generation capability to 3D using some kind of losses, including SDS or ISMs. So the advantage of this is they can exploit the generation power of SD, but the issue is that because they just use the SD as a inference model, so it's basically optimization based, which requires lots of iteration to generate slow generation. And because it is a single composition, so it doesn't have any interaction in consideration, so you cannot have like context or composition. So next field is learning-based hand-object interaction generation. And in this field, they generate hand-object interactions from text, and usually combined with template objects. The advantage is because they are learning based, so they have relatively faster inference speed, and it includes context awareness in their pipeline. But the weaknesses are they require template objects as input, and the outputs are non-photorealistic. They are just mesh-based, and they have limited generalization within their training data. So, for example, when we give an unseen object and unseen interaction as an input, so the existing method, something like text to H1, it usually generates H1 with some penetration and some implausible interaction. So the last one is trivial human object interaction generation. So this work generates human object interactions from text using the previously discussed SDS-based 3D asset generation pipeline. So they can generate photorealistic HY and you can generalize unseen interactions. But the problem is the previous works are null-based, which is one of the volumetry rendering techniques, which optimizes the voxel grid, which do not have mesh-based representation. So it cannot compute precise basic space optimization losses, something like iteration or content. So when we give interaction forms like this, it usually includes some severe penetration, as you can see on the right. So these were the brief discussion of the related fields, and I will explain individual papers that is related to our work. So Dream Fusion is the fundamental work for zero-shot 3D asset generation. So the test case, it generates 3D from text from using stable diffusion prior. So it proposes SDS loss first time. So it's an abbreviation of score distillation sampling loss. So the basic idea is when you render the image using some 3D representation, we put the rendering and we add some noise, epsilon, from normal distribution, which is a Gaussian noise. And we pass the SD pipeline, and it denoises the noise. So the basic idea of SD is to predict the original input noise epsilon, which is so SD predicts epsilon head by design. So it computes the difference between the predicted noise and the input noise. And we use this difference to calculate the SDS gradient. So by using this, we can compute gradient here, and the gradients flow back all the way to the 3D representation. In case of null, it's MLP, and in case of Gaussian, it's Gaussian function. So we can optimize the 3D representation using SD. Gaussian Dreamer is a later work. So it replaces the null with Gaussian splatty. And additionally, when they initialize the Gaussian point cloud, they use the existing text to 3D regression models, reconstruction in the set. So in their work, they use Shape-E, which is proposed by OpenAI. So by using these prior 3D reconstruction models, you can generate 3D assets in fast speed. The next work is text to HR, which is one of the previous publications of this lab. And this work is about generating end-object interaction in mesh from text and input object mesh. And the pipeline is basically DDPM-based network, which regresses the two-hand and object motion. The issues are it requires water type object meshes as inputs, and the outputs are non-photorealistic. And because they don't refine the motion after the genuine, they suffer from severe penetration, and because they are dependent on the trained data set, they are have limited generalization capability on scene objects. And the last related papers are interfusion and image UI, which are zero-shot human object interaction generation papers, and both of them use SDS and LORP to generate 3D HY in text. In case of interfusion, they first build a synthetic data set of HY by generating HY images using SD. So they build a synthetic data set of interactions, and they run the existing human pose estimator to extract the SMPL poses, and they build a pose code from them. And using the cosine similarity between the pose and the text input, text prompt, they can build a code loop for retrieving the pose from the text. And whenever they generate, they look at the code loop and extract the pose and initialize the human pose seamlessly. In case of DreamHY, it first generates the optimizes nerve volume, and after they converge to some degree, they estimate pose from the nerve volume. And from the estimated pose, they reinitialize the human nerve volume and then repeat the process. But most of them optimize nerve, which has limited visual fidelity and do not have mesh representation, which is hard to optimize physical losses, including penetration in contact. So I'm going to present the generating physically plausible random object meshes from text, which is a joint work of ELM and Professor Singerbeck. So in our test, our test is text, input is text, which describes the hand object interactions. And we expect to have an output that has below features, which is photorealistic and physically plausible, and which are 3D hand object interactions. So, so if we give a text prompt like a right-hand eat on a hamburger, we expect to have a 3D representation of a right hand grabbing a hamburger. But when you started this research, from the beginning, there were some challenges. So first thing was we don't have training data to make a learning-based model. So we cannot use like text to HY like method that learns the HY motion from training data. And secondly, so even if we just apply the existing zero-shot 3D generation methods, they don't have mesh representation. Even in case of interfusion or in case of like general Gaussian generation methods like Gaussian transform, they don't provide mesh. So you cannot optimize using penetration or contact losses. And the last one, even if we extract mesh somehow, those extracted mesh are very noisy because they are generated from the text. So they are non-order type. They have like self-intersection and bumpy surfaces. So whenever we optimize HY, they usually fail to have like plausible interactions. So we have like below motivations. So we firstly apply percent optimization approach, which is a zero-shot generation method using ESP. And secondly, we extract object meshes in robust manner for the later physics optimization. And we minimize self-intersection to enable robust optimization pipeline. So the contributions are like this. So we, to the best of our knowledge, this is the first work to photorealistic post-correct preserver 3D Troy mesh generation in zero-shot manner. And we robustly extract meshes with one-to-one correspondence mapping between vertex and Gaussians, which enables physics-based H1 optimization. And we additionally propose joint interpretation rules and create a guide translation one to further improve physical plausibility. And we empirically showed that we have superior visual realism with high physical plausibility compared to existing state-of-the-art. So our method is composed of two stages. The first stage is we independently generate object and hand vertex Gaussians from text. And after object and hand Gaussians are generated, we combine them using the initial H1 parameters. And we further refine those H1 parameters using vision language model and physics-based sources. So in the first stage, we use the existing SC-based sources, which is ISMOS. This is a variant of original SDS. So original SDS uses the DDPM and DDPM-based scheduler, but in case of ISN, it uses DDIM-based scheduler. In case of object Gaussians, it first just run the normal Gaussian generation pipeline, but at the middle, we extract the mesh, and then upsample to 400,000 vertices, and then for the hand Gaussians, we just use the existing one mesh model, which is upsampled 4 times. So when we extract meshes, we have to reassign 2 Gaussians, and those Gaussians should maintain the mesh topology after reassignment. So the natural and ideal approach should be just make a one-to-one correspondence between the mesh vertex and Gaussian, which is intuitive. And then to maintain that topology, we additionally apply Laplacian regularization on the Gaussian parameters, including position, color, and scale, which ensures consistent topology and prevents vertex decay even after they optimize. And during the object mesh extraction, we make a simple and robust approach of extracting object meshes. So first, we apply Poisson consumption, and we upsample the mesh to 400,000 bases. So originally, the previous works on Gaussian splitting, they usually find the Gaussians on the extracted triangles, which actually turns out to be very bumpy and noisy. So we remove these triangle binding files. And we additionally extract concise meshes. So because the original object mesh, the extracted object mesh, it still has some noisy inner surfaces. So to further prevent that, we additionally extract concise mesh from that, which is conducted by Bardes THOM sampling and alpha-shell reconstruction, which is used for the later physics-based optimization process. So as you can see on the right, from the several object mesh extraction methods, the alpha shape based reconstruction turns out to be robust compared to other methods. And interestingly, lightweight MR is a learning based mesh reconstruction methods, which also based on text generated object mesh. So after we generate object in M Gaussians, we finally initialize HY. So we combine the generated hand and object Gaussians, and the initial HY parameters are obtained from text to HY. But the initial text Y results are very unstable, and they often have severe penetration. So we need to further optimize them. So we employ several losses, which is very messy, and I'm going to explain one by one. So penetration loss is just a plain penetration loss, which is already used by text to HY, and also contact losses, which are also used by text to HY. But these three losses are not enough, actually. So when we naively apply these penetration and content losses, they usually just pull out the and then object each other globally. So it turns out to be non-contact and implausible interaction. So to prevent that, we additionally devise a loss term called reposition loss. So whenever there is a penetration on the finger side, so we expect the penetrating hand joint to be on the object surface. So we compute the distance between the penetrating joint position and the object surface, and we compute the relative distance, and we use that as repositions. And for consistency term, we try to we prevent the mode collapse from the optimization process, and especially for the hand poses, we constrain the XY rotation axis to prevent the implausible hand articulation. And when we compute these losses, we use concise object mesh we proposed earlier to enable robust vertex number estimation. And using these methods, we validate our pipeline on our proposed benchmark. So in our benchmark, we use 100 text prompts and 24 action types, which is quite larger than the previous works like Interfusion with 61 prompts and DreamHY with 12 prompts. And as evaluation metrics, we use two different criteria. First is prompt and 3D alignment, which includes clip score and T3 bench alignment. Clip score is intuitive, I don't have to explain, but T3 bench alignment is a evaluation protocol proposed by other previous work, which uses GPT-4 to automatically evaluate the alignment between the input text prompt and the 3D generation. And for physics metrics, we compute the penetration, contact ratio, and displacement measured by Python simulation. And as zero-shot 3D generation baselines, we use Dream Fusion, Polyp Dreamer, Gaussian Dreamer Pro, and S3D as baselines. And for zero-shot 3D human object interaction generation baselines, we use Interfusion and DreamHY. But because these are originally designed for human-object interaction, we adapt further to generate hand-object interaction. So as a quantitative results, in terms of play score, we have 2.3 improvement over the second best, which is Prolific Dreamer, of 29.1. And in terms of history line, we have 0.7 improvement over the second best, which is Hash3D 1.9. And to be clear, to clarify, the maximum score of history line is 5. And in case of physics evaluation, we have smallest iteration and maintain the high contact ratio, and we also have smallest simulation displacement compared to the baseline test H1 in the GO. As qualitative results, when you compare with existing 3D generation methods, they are unable to generate compositive HY because they are not designed for this task. So easy win. And but also for human object interaction baselines, these two columns are from the original implementation. So these are from the human object interaction pipeline, and these are from our adaptive hand object interaction pipeline. So for the human object interaction, in case of interpretation, they have severe penetration, and in case of GMHY, because their pipeline includes the reinitialization of their volume using pose estimation. They fail to reinitialize the human part. That's why they don't have like valid human. And in case of the hand version, interfusion has severe penetration and various artifacts. And in case of GMHY, they again fail to estimate the hand, so they don't have hand in case of headphones. In case of cover copy, they have vague hand volume, and also for hand rubber, they don't have like visible hand. But for our case, we have clear distinction of object and hand, and also have lots of interest. For evaluation, we evaluated proposed components one by one. In terms of clip score, if you don't apply Laplacian, the clip score drops by 1.0 because of jittery surfaces and color drift. In case of reposition nodes, if you don't apply that, we also see the clip score dropping. And for the physics-based optimization and visual language model requirement, in case of physics optimization, we have major improvement of clip score and also for the displacement. And for visual language model requirement, we have a huge improvement in terms of T3 line, and we still maintain the contact ratio and displacement. And in case of the visual language model requirement, I realized I didn't explain my lesson. So visual language model requirement works like this. So we give input rendering like this, and we prompt the VLM to select the best class of interaction among the multiple candidates by enumerating the hand translation in XYZ axis. So among like 125 candidates, they select the best one, best sample, which turns out to be semantically plausible and aligned with the input prompt. So in case of the smartphone, the initial HY generation from text to HY doesn't have valid context, but after VRM refinement, they have visible context. And in case of hammer, the initial HY, it doesn't grab the hand doesn't grab the hammer properly, but after VRM refinement, can publicly reach the, you know, in case of the bear, the initial result has severe penetration of the thumb region, but after requirement, it has less penetration. So as extra analysis, we have interesting findings. And in case of user study, we got the participant saw our method as the best visual quality and physical plausibility. And we additionally conducted evaluation experiment on priors that not help refining the HOL. So when we don't apply any prior in physics optimization, which only includes the physics-based losses. So in case of that, it has 31.3 CLIP-score. But if we apply other existing priors like CLIP or SDS variant ISM or multi-view ISM, they all decrease the CLIP-score. So when I check them qualitatively, they usually separate the hand and object away, which basically results in no contact at all. But in case of bearing bond, it which is a 0.1 increase in CLIP-score, but it increases the TCR alignment by 0.6, which is interesting because normally we think like if we just apply CLIP and SDS, that's all good to go, but which is not. And in conclusion, we propose the training framework for photorealistic and physically plausible 3D HY context. And we use vortex Gaussian correspondence mapping, which enables reliable mesh instruction and topological regularization. And our contact physics losses and joint reposition and VR requirement further boost the interaction plausibility, and we achieve state-of-the-art visual realism, text alignment, and basic plausibility. But there are still several limitations in this work. The critical one is because it still relies on per sample optimization pipeline. It has long generation time compared to learning-based methods. So either we can find the efficient diffusion guidance to reduce the optimization loop, or we either make a large scale data set and just train the learning-based methods. So this is the end of presentation. Thank you. And if you have any question, please let me know.
Okay, I have one question. So regarding the VLM environment, so are you getting the graphing from the regions or just people's variance to pick the best one? Maybe the
Yeah.
so why not doing the
In case of the obtaining gradient, so I actually try to find the papers that obtains gradients from the visual language model. But at the time, which was like last year, there was no accepted paper, which are mostly archive papers. So for this test, because it's optimization based, there is very little difference between iterations. But for learning based approach, which iterates over different samples, in case of that, the VLM gradient can be helpful. But in the per sample based optimization, I think it'd be challenging to include the gradient based VLM as a guidance.
So if you're saying that nowadays, there is that getting some progress.
I recently saw some VLA papers that uses VLM as guidance. In case of that, so those are mainly reinforcement learning papers. So in case of that, they query the VLM, and then VLM outputs the reward score. So which means that VLM is basically a reward function. So in case of that, VLM serves as some type of loss function or guidance that can be interpreted as giving a gradient.
Thank you. Okay, so there's not being more attention, so that can be you. Thank you.